Okay, let's look at how we create a probability histogram. Remember that the probability histogram came from a probability distribution table. And in the first column of the table, we have the values for x, the random variable x. In the other column, the second column, we have p of x, the associated probabilities. Okay, the values for x, remember if we're guessing on a multiple choice test, the possible number of questions that you could get correct are 0. You can get 0 correct, you can get 1 correct, you get 2 correct, 3 correct, 4 correct, or 5 correct. So success in this problem means getting the answer correct, and x can take on any number from 0 to 5. And that becomes the first column of the probability distribution table. To answer the probability, to find p of x, we have to calculate the binomial probability when x value, or the number of successes, is 0. So letting the number of trials be 5, the probability of success is 1/4 or 0.25, s equals 0. So you go to your calculator and you plug those three in and you get 0.2373. So let me just demonstrate. Second, DISTR. Binom PDF. 5 1/4, and change this to a 0. And hit enter on paste. Okay, 0.2373. Now pause the video at this point and take a minute and do that for all the values of x. Okay, so this was just a value of x equals 0. Do it for x equal 1, 2, 3, 4, 5, and 6. So just to get you started, second DISTR, go to Binom PDF again. Okay, you're going to change that 1 to a 0, that 0 to a 1, and that would be the answer for an x of 1, p of 1, basically 0.3955. And you're going to do that for a probability of 2, 3, 4, and 5. Okay, so those are the differing values of s with the differing values of x. Now, the collection that you get after this is called a binomial distribution. Okay, so take a minute and do that. Pause the video and complete those values. So you'll have 6 probabilities. Okay, your 6 probabilities are 0.2373, 0.3955. This is the probability of getting 1 correct when you guess on a 5-question multiple choice test. The probability of getting exactly 2 correct when you guess is 0.2637. The probability of getting 3 correct when you guess, we did this is part A, 0.0879. The probability of getting 4 correct, 0.0146. The probability of getting 5 correct, we did this on part B, 0.0010. Okay, now these probabilities right here are called a binomial probability distribution. It's a collection of probabilities that are the outcome of a binomial probability experiment. These are all the values of x, and these are all the values for p of x. Now from the last lecture, you should recognize the 2 columns. Now those 2 columns can be placed into a histogram if we label the horizontal axis with values of x. So if we look at these values of x horizontally, we have 0, 1, 2, 3, 4, 5. We're going to center the values of x beneath the rectangle right in the center. And the height of each rectangle represents the probability of that event happening. Now, I'm not going to expect you to do this on the calculator. This is not something you should do on the calculator. You can do this on paper. You're just going to, on the horizontal axis, put your values of x, and on the vertical axis, make each bar the height of the probability of that event happening. So each value of x is associated with a probability, which is the height of the bar. Now, I approximated the height of this bar around somewhere between 20% and 30%, about 23%. Is that what it was? Yep, 23.73%. It's a little bit halfway between 20% and 30%. So this is an approximated image, but this is a histogram based on the probabilities from the previous problem. Now you can answer questions by just looking at this histogram. You can answer a question like, what's the probability of getting two answers or two questions correct? You would look at x equal 2. You would look at the probability, which is the height of the bar. And if the vertical axis were clearer, you can see exactly what that was, which here it was about 26.37%. The shape of the distribution, you should recognize that it's kind of skewed to the right. Okay, the shape of the distribution is skewed to the right because there are a few high values of x, C, 4, and 5, that pull the distribution tail further out to the right. So this tail is being pulled, dragged to the right, where the bulk of the data is really on the left-hand side. Okay,